So, Sn1 and Sn2. And you guys don't mind me monologuing, because the more I monologue, the less stuff we get to in front of the exam. So, win-win. We have talked about how whether or not a given starting material will go through the Sn2 pathway versus the Sn1 pathway depends on the relative heights of these transition states. And the transition state for the Sn2 reaction depends on two things. It depends on the nucleophile, and it depends on the structure of the alkyl halide. That's a nomenclature term. I've had some people in office hours ask about it. It just means the functional group where a carbon is attached to a halogen, an alkyl group, a hydrocarbon attached to a halogen. In our example last time, it was methyl iodide. So these two things influence the height of the transition state for the Sn2 reaction. The nucleophile, as we said, good nucleophiles make the Sn2 reaction faster. In other words, they lower the activation energy or lower the transition state. Primary and methyl alkyl halides react very quickly in Sn2 reactions, whereas tertiary alkyl halides react slowly or not at all. Right? And we drew this in last time's notes, so I'm not going to reproduce it. For secondary alkyl halides, it's somewhere in the middle. It's a little bit slower. And whether or not you go through Sn2 or Sn1 for a secondary alkyl halide is really going to depend on what the nucleophile is. All right? And we said the reason for this is sterics. The more alkyl groups you put behind the leaving group, the less likely it is for a nucleophile to be able to get in there and reach the sigma star. Okay, so we haven't talked about how the rate of Sn1 is affected by the nucleophile and the alkyl halide. And I guess we could say that the nucleophile doesn't influence the rate of Sn1 directly, because the rate of the Sn1 reaction, remember the rate law we drew, is only dependent on the alkyl halide and not on the nucleophile. So we'll see nucleophile affects the rate of Sn1 reaction primarily by favoring the alternative Sn2. Good nucleophiles are reactive enough that they're not going to wait around for the leaving group to leave, unless, of course, they have to, if it's a tertiary alkyl halide. That being said, the structure of the alkyl halide influences the rate of the Sn1 reaction. So if we had, let's see, methyl, primary, secondary, and tertiary, all of these reactions are slow, but we'll say there's no Sn1 for methyl and primary. It's slow for secondary, and it is less slow for the tertiary alkyl halide. I'm using those terms because I don't want you to get the idea that the Sn1 reaction is fast. It's not. It's slow because you have to wait for the leaving group to leave, and that's an uphill energy step. But for all the available options, it's fastest for the tertiary alkyl halide. And we need to talk about why that is, why it should be faster for the tertiary alkyl halide than for secondary, and so on. But before we go on, questions? Anyone ask? Okay, yeah, go ahead.
So would it be more favorable to have like a second degree Sn2 or like the second degree Sn1?
Yeah, so the question is, what if you have the secondary alkyl halide and is it going to go through an Sn1 or Sn2 mechanism? That's going to depend on the identity of the nucleophile. Good nucleophiles aren't going to want to wait around, so cyanide will replace iodide in an Sn2 fashion. In contrast, if instead you want to use a weak nucleophile like water, you can get the reaction to happen, but it will be slow and it will proceed through Sn1. So our ability to navigate the mechanisms of these reactions is going to require us to reflect on the quality of the nucleophile and the structure of the alkyl halide. And once you have those two things in place, you should be able to figure out what happens. Others? Okay, well, let's talk about how do you know if a nucleophile is good or weak? At home in the chat, we said that good nucleophiles, this is from last time, good nucleophiles have conjugate acids with pKa's greater than 0. So not on the list of good nucleophiles are water and alcohols because their conjugate acids have pKa's of -2. All right. So for a moment, I'm going to shift away from this three-dimensional energy surface and instead just focus on the Sn1 reaction pathway. So we'll call this Sn1 completeness. It's neither one of those axes above. We'll have, let's see, I'll stick with purple. We'll have starting material here, transition state 1 here, carbocationic intermediate, and products here. Starting material, products, carbocationic intermediate, and transition state 1. Okay. So in order to understand why the rate of the Sn1 reaction varies like I showed you, I'm going to copy and paste this for our discussion. We need to consider the relationship in structure between the transition state 1 and the carbocationic intermediate. And the principle that we're going to use is something that's described in your text as the Hammond Postulate. And I don't know that, I don't really think you need to remember that that's its name. Sometimes naming things just makes them worse and more difficult to remember, and this may be one of those times. The principle is simple. Two adjacent positions in an energy diagram are similar in geometry if they are close in energy. And you may look at that and say, well, duh. Two positions on an energy diagram that are adjacent to each other, if they're close to each other in energy, they must be close in geometry. What we would say then, because of this Hammond postulate, and the reason behind the Hammond postulate is just that changing structure requires energy to change. So if you change the structure dramatically, the energy should also change dramatically. So if two places on the energy diagram are adjacent to each other and close in energy, they have to be similar in structure. The conclusion, the so what here is that the transition state 1 resembles the carbocation in structure. Okay. I'm getting tripped up with first vision type language about the carbocation resembling the transition state structure in features and likeness and all of that stuff. But In any case, they are similar in energy, therefore similar in geometry. We will say transition state 1 is carbocation-like. And interestingly, we already said this when we drew the transition state for the Sn1 type reaction, where we had the leaving group leaving before the new bond comes in. That would lead to a buildup of positive charge on the carbon, and the geometry of this transition state or near the carbon should be not tetrahedral anymore, but perhaps not totally sp2 hybridized planar and so on. So it's somewhere between those two, but the key point is there's a buildup of positive charge on the carbon where the leaving group was. And what this means is what lowers the energy of a carbocation will also lower the energy of transition state 1. So that's an important connection, because it allows us to reason through the stability of a carbocation, and that what we learned there will be reflected in how high or low in energy that transition state is. Okay, so that's a bit of a chain of logic and explanations. Any questions about that? Yeah.
So the transition state is with the dotted line, correct?
The transition state is with the dotted line here, yeah.
And so why is it higher in energy? Because I guess just reasoning through, I would think the iodide ion would share some of the electron density, and so it would be less unfavorable than the energy minima with the complete carbocation.
Yeah, so the question is, why is the transition state higher in energy than the complete carbocation? And the reason has to do with the fact that this carbon is not totally planar. So you lose the benefit of having the bond. It's already disappearing. But you've still got the repulsion from having the protons not completely trigonal planar. Remember, geometry in molecules is a function of getting things as far apart as possible. And so when that carbon was bonded to 4 things, tetrahedral was as good as you could get. Suddenly, as the iodide leaves, that's no longer the case. And so the downward slide from that transition state is relaxing into a trigonal planar arrangement. And so I haven't been following the chat perfectly closely, or even sort of closely, but Jessica at home is stating that having a better leaving group should lower the energy and lead to a faster reaction rate, and that is true, yes. All right, others? Yeah.
So if I'm understanding you correctly, if something is more, if a molecule is more spread out, that means it's lower in energy. Like, because if it's tetrahedral, like they're further, all the molecules are further apart from each other.
So yeah, the question is, if a molecule is more spread out, is it further in energy? Well, yes, but it's not necessarily fair to compare tetrahedral to a trigonal planar carbocation, because you've changed the number of bonds that are present.
But just like in this example,
Yeah.
they're not like, they haven't spread out as far.
That's
as
right.
they can, like,
Yeah, in this example, those carbon-hydrogen bonds have not spread out as far as they can, and you've already lost most of the benefit of the bond. So yeah, the downward slide is relaxing into that planar structure. And yeah, I think that's a point that's coming up multiple times on the chat, so let me say that again. In the transition state, you've got the leaving group basically gone, and you've got a buildup of positive charge on the carbon, but these bond angles are still not 120 degrees. The carbon-hydrogen bonds are closer to each other than they are in the planar carbocation, and there's electron-electron repulsion between those bonds. Okay. All right. So let's talk about carbocation stability and what makes one carbocation more stable than another. And we're going to quickly encounter our old friend hyperconjugation, which I'm imagining eye rolling and groans. Hyperconjugation is the golden child of the why question in OChem. You get sort of sick of him, always sick of him or her. Do we need to assign gender to an idea that we've just personified? Probably not. You get sick of that idea in the same way that you sort of get sick of Nephi telling you that he's large in stature. Is it bad that as I get older I identify more and more with Layman and Lemuel? All right, so it turns out that methyl cations are less stable than primary carbocations, which are less stable than secondary carbocations, where we replace two of the three groups on the trigonal planar carbon with non-hydrogen things. And then that is less stable than the tertiary carbocation. And that's a rule you can choose to memorize. Although memorization, though it has its place, as we talked about, in a world where you can just look things up, it may not be the most useful thing you can do. And so we want to understand why. And if you understand why the tertiary carbocation is more stable, there's a whole host of things that are going to be way easier for you in chapters 9 and 10 and even 11. So this is an important concept. Yes, tertiary carbocations are more stable than primary or methyl carbocations. And the reason, dun, 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 is hyperconjugation. So let's look at what happens. And we've used this actually before. We used a carbocation as our first demonstration of what hyperconjugation is. I'm going to just draw a primary carbocation. These two hydrogens and this carbon are all in the same plane. Bond angles are 120 degrees. The carbon is positively charged. On that carbon is an empty p orbital. You're used to looking at positively charged carbons that are sp3 hybridized as having an empty p orbital, and that's certainly the case here. I need slightly larger font. We're using color here simply to reflect the sign of the wave function. There is a node at the nucleus of carbon, that's why, and in the plane of these atoms, where wave function goes to 0. We don't care if it's plus or minus here or here, just that they're opposite. And the carbocation provides a situation in which that empty p orbital can line up with and mix with an adjacent filled carbon-hydrogen sigma bond. So this is what a carbon-hydrogen sigma bond looks like. You have a large lobe that encompasses the hydrogen. You have a node at the carbon, and then opposite phase lobe on the other side. So when you have an empty orbital that can line up with a filled orbital, you can mix them together through our typical MO mixing program. And you mix them together and you get two options out. The plus option is what you would get. It would actually look just like this, although maybe we want to draw it a little bit more true to life so you can get a sense for what this actually looks like. In the plus option, it would be like the carbon-hydrogen bond we're spreading out a little bit onto the adjacent positively charged carbon. The electrons in that bond get to experience 3 nuclei instead of 2, and they get to spread out, which is always delocalizing. And so electrons from that carbon-hydrogen bond move lower in energy. We call that stabilization due to delocalization. Lots of TIONs there. And that's where the benefit of hyperconjugation comes from. The other consequence of hyperconjugation in the carbocation that we'll talk about is that the LUMO spreads out, and you see the LUMO spreading out from the minus combination. I'm going to get rid of the circle so you don't think we're dealing with charge. The minus combination doesn't have electrons in it and looks basically like the option where some of the LUMO is now out on the adjacent carbon-hydrogen bond. Most of it is still on the carbon, but some LUMO now is on the adjacent carbon-hydrogen bond. Okay, that hopefully is a bit of a review. Go ahead.
Will the carbocation do hyperconjugation with the other carbon-hydrogen bonds, or just that one because the other ones aren't like that?
Will the carbocation do hyperconjugation with those other bonds? The answer is yes. I haven't included it for simplicity's sake, but this orange or yellow lobe will probably encompass those hydrogens on the bottom as well. And there would be a blue lobe encompassing these. Of course, the mixing is better when they're lined up exactly parallel, so it's better mixing here than involving these bonds, which are sort of straddling or staggered relative to that p orbital. All right, so just to review, this is the sigma plus p option. This is the sigma minus p option. This is the LUMO that's spread out. So hyperconjugation is stabilizing because it allows electrons to spread out and move to a lower energy level. It's true that we also make an out-of-phase option, but who cares because it's empty. So as you introduce more alkyl groups, you have more chances for sigma to p hyperconjugation. And that leads to more stability. Okay? Questions you want to ask about that? All right. So now applying what we just talked about for the Hammond postulate, if going from primary to secondary to tertiary lowers the energy of the carbocation, going from primary to secondary to tertiary will also lower the energy of the transition state and will accelerate the rate. That's probably, we could probably just say it will accelerate the Sn2 mechanism. I'm sorry, thank you. I hate it when I do that. I had one job there in that sentence. And going from primary alkyl halide to secondary to tertiary doesn't change the energy of the starting material much, but does lower the energy of the carbocation intermediate and the transition state and makes it faster to do Sn1. Okay. Okay. So we could actually maybe modify our horrible drawing here. Instead of for a methyl halide, let's modify it for a tertiary alkyl halide. I'm not sure whether I have any business doing this, but what the heck. I think I'm going to need to erase some purple lines and some blue lines. We'll erase some transition state stuff. Why didn't I just start from scratch? Well, okay, now that's seeming a little bit more reasonable. I'm erasing tons of stuff. Okay, so we said that let's have these 2 points be our transition state and our carbocationic intermediate. And this point will be the energy of the Sn2 transition state. Going from primary to secondary to tertiary increases the energy of the Sn2 transition state. So where we used to be is here. Now we're here. So if I were to draw the Sn2 mechanism or the energy diagram, now I've got a taller hill to get over. So the Sn2 rate is slower. In contrast, going from primary to secondary to tertiary should lower the energy of the transition state and lower the energy of the intermediate. So here we are at our new points. And I've tried to make it so that if you compare the relative barrier heights, I didn't quite make it bad enough, did I? For there to be true contrast. All right, so by having a more stable carbocationic intermediate, it is now faster for us to go over the transition state 1 to get to the intermediate and then downhill to products. Just because we've changed the structures of the starting material. All right, yeah.
So therefore, the Sn2 is no longer favorable for a specific reaction to have, for example, tertiary.
Right. That's why we say there's no Sn2 for tertiary alkyl halides, because that pathway is too high in energy to be reasonable. It's too slow. In contrast, now for tertiary alkyl halides, the Sn2 or the Sn1 transition state 1 for the Sn1 reaction is now low enough in energy that we can actually see it happen. Yeah.
This is way off base, just ignore my question. But if you change the starting materials not by the molecules themselves, but by like stereoisomers, how would that change these?
Okay. It's a good question. If you change the starting material, not necessarily by changing the substitution of the carbon that bears the leaving group, but instead try a different stereoisomer, how would that affect things? If there were 2 enantiomers, the reactions would have to be exactly the same. The reaction of one enantiomer should be exactly the same as the reaction of the other enantiomer in terms of energy. If they were 2 diastereomers, it might be different, and we'd have to examine the situation. Okay, other questions? So one thing that you should ask me is, all right, these lovely drawings are fun, but how the heck can you even tell whether the mechanism has been Sn2 versus Sn1? It's not like you can pinch and zoom out with molecules until you actually see them. I mean, maybe someday we're going to upgrade to that capability, who knows, but at least at this point, you can't zoom in that far to watch things going on. You can, of course, do calculations, and that can be fun, but what about experiment? How can you tell whether a reaction has been Sn1 versus Sn2? And the key has to do with that structure of either the transition state or the intermediate. Recall that the transition state for the Sn2 reaction looks like this. The nucleophile approaches the carbon from the opposite side of the carbon leaving group bond, because that's where the LUMO is, that's where the sigma star is, and because that provides the transition state where the nucleophile and the leaving group are farthest apart, and that minimizes steric repulsion. So what does this mean for a starting material where the leaving group is at a stereocenter? Let's okay, we've made ourselves a secondary alkyl halide there. And we're going to use a good nucleophile. This time let's use maybe a thiolate, negatively charged sulfur alkyl sulfide that's conjugate acid, has a pK of about 8, so it's on our list of good nucleophiles. In the Sn2 reaction, what we would expect to have happen is lone pairs on the sulfur attack the carbon iodide sigma star. If we were to draw where that sigma star is, we would see a lot of it pointing out behind the carbon iodide bond. And then we would see a node in between the two nuclei. That's how you can tell it's an anti-bonding orbital. And another large lobe on the other side of the iodide. We've already discussed why the nucleophile attacks at carbon. So we have to attack on the backside because that's where the sigma star is. And because the reaction is concerted, as I start to decrease this distance between sulfur and carbon, an interesting thing happens, and that is that the substituents on that carbon start to move away from the incoming nucleophile. They're repelled by it. So we eventually reach a transition state that looks like that carbon is basically trigonal planar. You know, I mean, bond angles here would be around 120 degrees. It's basically sp2 hybridized. Here is your nucleophile coming in, as I said, from the backside. Here is your iodide leaving from the front side. And as iodide continues to leave, these groups are going to continue to be pushed away from the incoming nucleophile, such that when the reaction is completed, this is what I've got. So we've switched the side that the heteroatom is on. And this process is called inversion of configuration. It would be tempting to say that this means that whatever is R goes to S and whatever is S goes to R, though that would depend, of course, on the identity of the nucleophile and the leaving group and various priority rules. So I really can't generalize in that way. But if I were to redraw this molecule in a maybe slightly different way that has the stereocenter the exact same way, once I put the sulfur on there and it replaces the iodide, this is my product. I used to have stereochemical configuration where iodide was down. Now the nucleophile that replaced it is up. Okay? So this is called inversion of configuration. And it means that if you take a chiral and enantiomerically pure sample and you run an Sn2 reaction with a good nucleophile, you're going to get a chiral and enantiomerically pure product. You retain what we call stereochemical information. The configuration is different, but you had a stereocenter in the starting material and it was all of one configuration, and in the product you still have a stereocenter and it's all of a certain configuration. All right. That can be somewhat difficult to see. And yes, by enantiomerically pure, I mean only the product has only this stereochemistry. All right, questions about what we mean by inversion of configuration? Yeah?
How did we know it's going to be an Sn2 reaction as opposed to an Sn1?
Okay, how did we know it would be Sn2 versus Sn1? Well, I'm showing you the data and you're inferring that it had to be Sn2. But in terms of predicting, you would know this is a secondary alkyl halide. We would know that Sn2 is slower for secondary. It's also slow for, secondary is also slow for Sn1. So then we're going to simply consider the nucleophile. And if it's good, we're going to prefer Sn2 versus Sn1. Yeah?
So technically this molecule, if it's pure, has no other combinations.
Yes, if this is enantiomerically pure, I only have this enantiomer. We can go ahead and assign stereochemical configuration. This one is S, and it just so happens that this one is R. Because we replaced the highest priority group on one stereocenter with another highest priority group, but we did it from the backside, so stereochemistry switched. Okay, other questions about inversion of configuration? So that is always a consequence of Sn2. If on an exam, for example, you had, and I'm choosing just a simple molecule with a stereocenter, but if on an exam you drew this, even if you said it was Sn2, this is wrong. And you're going to get the question wrong, because with an Sn2 reaction, there must always be inversion of configuration. So let's go ahead and put the big X through that and show you what the actual Sn2 product would be. And we'll put a green smiley face by it to indicate that that is correct. All right? If you don't draw the right stereochemistry in your Sn2 product, it tells me you don't fully understand what the Sn2 mechanism is, because you haven't mastered that it has to happen through backside attack with inversion of configuration. And that's how we tell that something passed through an Sn2 mechanism. The stereochemistry is evidence of that. Now, I will show you the consequence of an Sn1 reaction on this same molecule. We're going to use a secondary alkyl halide, and then we're going to use something that is just a weak nucleophile. In this situation, the barrier to SN2 is too high, and so the weak nucleophile has to sit around and wait until we go through a planar carbocationic intermediate. Then the nucleophile can add from either side, and ultimately we get both enantiomers of the product. We go through a planar achiral intermediate. And if you go through a planar achiral intermediate, from that point on, ever after, if you make a stereocenter, you have to make both varieties. Okay? The planar intermediate can be attacked from above or below, and that's how we get both of these products. So we need to end there, and we will talk a little bit more about that next time.